All right, in this video, we are going to work through the following indefinite integral, and it is the inverse, sorry, the indefinite integral of cosecant of x squared divided by cotangent of x dx. All right, and so this integral is not a basic one. It's not just a simple derivative fact that we need to do in reverse. It's more complicated than that. And so this one is going to be a substitution problem. Okay, so looking at good choices for u, right? If I look, I can see that there's nothing really that looks like it's inside anything else. Okay, there's an x, right, that's inside, but remember u equals x is never a good choice for u, because if that works, that means you didn't have to use substitution. It means that it was a basic integral most likely, and you missed that fact. Okay, so that's not valid. There is basically an inside part here with the cosecant, right? Remember, because if you have this cosecant squared notation, that is the same as cosecant of x squared, like this. So this notation kind of obscures the fact that that cosecant is inside, really inside something else, right? But it turns out that is not really what you want to pick to be the u in this case, the cosecant squared. So in this case, it's probably good, right, that is obscured. All right. So just looking at it, there's nothing really that looks like it's inside, even though this cosecant is. If you look at the choices for other good choices for u, right? One of the things I said is that a good choice for u is something whose derivative appears as a factor, right, of the integrand. Okay, and so cosecant, if I take its derivative, right, that's minus cosecant cotangent, right? I do have another cosecant up here, but this cotangent is down in the bottom parts, right, of this fraction. So really, it's more like a tangent. And then the derivative of cotangent is minus cosecant squared. All right, so you can see, hey, wait a second, cosecant squared appears on the top as a factor, right? So there's really, really nothing I would have to kind of finagle or mess with. So that's looking pretty good, right? And then on the third thing on my list of good choices for you that I talked about in the introduction substitution video, were good choice for you would be the denominator. That might work out as well. And so you can see the denominator here is cotangent x. And so there's a couple of things, right? The fact that it's in the denominator and the fact that its derivative, or almost its derivative, and by almost I mean a constant multiple of its derivative, appears as a factor of the integral. That's going to lead us to saying that we should pick cotangent of x, right, as a good choice for you. Okay, so then we would calculate our du, and the derivative of cotangent is minus cosecant squared x dx. And you can see, hey, we are off by a constant multiple here. We have a minus cosecant squared x, and we don't have one here. That's easy to fix, right? Because what you would just do is multiply both sides, right, of this second equation by cosecant squared, or by -1, right? And on the left side, you have -1 du. Notice this side still only has the values of u in there. On the right-hand side, you have cosecant squared x dx. So all x's over here, all u's over here, and that's exactly what I have in my integrand. And so that looks really, really good. All right, so now then I'm going to go make the substitutions. Before I do that, right, it's probably helpful if you pull this apart a little bit, right? For cotangent x, that's easy to substitute for because that's what you pick to be u, right? If I um, just cotangent x is u, so this is just going to be 1 over u. The cosecant squared x dx, though, that gets a little bit more confusing for people, but really that can just be pulled off over here to the side and written like this, like so, cosecant squared x dx. Again, as I've mentioned in some previous videos, if you don't realize or that looks fishy to you, right, then remember you can always write cosecant squared x as cosecant squared x over 1, right, and then multiply these fractions together. Cosecant squared x times 1 is cosecant squared x. 1 times cotangent x is cotangent x. So multiplying these two fractions gives us exactly this expression right here. So they are exactly equal to each other. And then if I have some expression over 1, well, I don't really need to write that, right? Because of the fact that anything divided by 1 is just itself, right? And so this expression is exactly equal to this one here. Okay, so now it's really easy to see how the substitution is going to go, right? For 1 over cotangent, I'm going to have 1 over u, and cosecant squared x dx, that's exactly whatever I have over here on the right-hand side. I know that in terms of u, that would be exactly equal to -1 times du, okay? All right, and so now I have switched every single occurrence of x over to some expression involving u using these equations here. And so now you can see this is a much simpler integral, okay? And it's going to turn out to be one of the basic facts, all right? First off, I have a constant in here, and using the constant multiple rule, I can rewrite that as that same constant, -1, which I'm just going to write as a minus when I pull this out, times the integral of 1 over u du. All right, and then the integral of 1 over u is the natural log of the absolute value of u. Don't forget the absolute value, plus c, okay? And that's just a basic integral fact, okay? One of the basic derivative rules in reverse, okay? All right, and now we're just left to back substitute. We want our answer to have the same variable as in the original, and so back substitute cotangent x, right, for u, and so the final answer on this one is the opposite of the natural log of the absolute value of cotangent of x plus some constant c.